In this video, I'm going to show an example problem based on Fourier series. The problem we're looking at is we're asked to find the Fourier series of this periodic function f with period 2 pi, and on the info minus pi to pi it's defined as follows. So it's x squared on the negative half of the interval from minus pi to 0, and pi times x on the positive half of the interval between 0 and pi. So let's just have a quick look at the computer just to get an idea of what function we're dealing with. I'm on a Sage worksheet here on CoCalc using the Python language. So I've got a couple of plotting commands here. I define capital P to be the plot of x squared over the interval minus pi to 0, and I add to that plot, capital P, a further plot of pi times x over the positive half of the interval. And when I execute this, we get what we're expecting, the graph. So it's x squared on the negative half, starting up here around the value pi squared, goes down to 0, and then on the positive half it's this straight line pi times x, and it returns to the value of pi squared at the end of the interval. It's a continuous function over the whole interval, although it does have a non-smooth point here, because if you think of the derivative of this function, as you approach 0 from the left, the derivative is approaching 0, but then it instantaneously jumps to a derivative of pi on the linear part. So the first derivative isn't continuous everywhere. It's got a discontinuity at 0, but the function itself is continuous. And it's got the same value at the start and end of the interval, so it will be continuous when you think of it extended as a periodic function across the whole number line, although there will be another point of discontinuity in the first derivative of the function at these endpoints here. So let's just have a look at the function and see what we're dealing with. So we'll return now to what we're writing on the paper. So the Fourier series will be, well, so this is what Fourier series looked like. It's an expression for the function involving a constant term, and then these two infinite series of cosine functions, cosine nx, and a similar infinite series involving sine functions. The sum from n equals 1 to infinity of bn times sine nx. So the constant function 1, the cosine nx functions, the sine nx functions, those are the Fourier basis functions. And the theory of Fourier series says that we can express any reasonably well-behaved function in such a way. So the problem we've got to work through here right now is we've got to determine what those what the values of those coefficients are in order in some nice computable way, so that we can put down the Fourier series and compute with it and compare it to the original function. So where the coefficients, so the standard formulae that we looked at in the unit for each of these coefficients, they're kind of inner product formulae between the original function f and the relevant basis function. So the constant coefficient a0 is 1 over pi times the integral of just the objective function itself. And for n bigger than 1, the coefficient an, it's like the inner product of the function with the cosine function. So it's the integral of f of x times cosine n of x dx. And similarly, the coefficient bn is 1 over pi times the integral from minus pi to pi f of x times sine nx dx. So these are standard formulae for these coefficients, so we need to evaluate each of these in turn. We'll start with the constant coefficient a0. I won't repeat the formula, but this is it here, so we have to do this integral. But of course the function is defined in two different ways, on the negative half and the positive half. So it makes sense to split it up and say it's the integral over the negative half plus the integral over the positive half. Split it up like this, so I should have put in the definitions there, but so this is the integral from minus pi to 0 of x squared dx, and this is the integral from 0 to pi of pi x dx. So what does this give us? Well, integrating x squared gives us x cubed over 3, and you evaluate 0, you get nothing. Minus pi, you get minus pi cubed over 3, which is subtracted again, so it becomes plus pi cubed over 3. And then down here, this integrates to pi x squared over 2. You don't get anything when you evaluate at 0, and you get pi cubed over 2 when you evaluate it at pi. And cancelling the pi and bringing these two fractions together is going to give us 5/6 of pi squared. So that wasn't too bad. So that's the constant coefficient, 5/6 of pi squared, or it's twice the constant coefficient, because in the Fourier series expression here, there's an extra factor of a half that we need to multiply by that when we're forming the Fourier series at the end. Okay, so slightly harder then is the coefficients a n and b n, but we'll launch into one of these. So again, we have to do this similar trick here of splitting the integral up across the two halves. So an is going to be the quantity 1 over pi times the integral from minus pi to 0, and on the negative half, f of x is x squared, so the x squared times cosine of nx dx. And then on the positive half, again you got the 1 over pi, the integral from 0 to pi. On the positive half, the function is pi times x, and again that's multiplied by cosine nx dx. So we have to do these two integrals. They're not too bad. They're products of x with a cosine, so you would need to use some kind of integration by parts to do those. But just to speed us up a little bit, I'll jump across to the computer again, and we'll use the computer to just quickly tell me what these two integrals are, rather than me trying to work through it. So first of all, we're integrating x squared times cosine of n times x, integrating that with respect to x. And then the second one, I want to show the answer to integrating just x, or well, we had a pi inside there as well. Okay, so the computer shows me the two integrals there. So I'll return to my paper, and we'll put down the results of those two integrals. So we're doing integration by parts. Integration by parts from Sage. You can do similar calculations with MATLAB as well, using the symbolic differentiation. So from this first integral, we get this expression. So we get 2nx cosine of nx plus n squared x squared minus 2, and that's multiplied by sine nx. The whole thing is over the denominator n cubed, and this gets evaluated at minus pi up to 0. And then the result of the other integral is 1 over pi, and that second outcome there was pi times nx sine nx plus cosine of nx, and that's all over the denominator n squared. And this is evaluated at 0 to pi. Okay, so things are starting to get a little bit complicated, but just look at the kind of things that are going to happen when we do this evaluation. Anywhere you get a factor x and you're evaluating at 0, of course that won't make any contribution there. And as well sine nx. Now when you evaluate sine nx at any integer multiple of pi, including 0, of course you always get 0. So those signs actually won't end up making any contribution. And the cosine nx factors, when you evaluate those at a term n times x, you're always going to get plus or minus 1, depending on the parity of n, whether n is an odd or even integer. So this will simplify somewhat. Lots of these bits will be zeros at various times, and then we also expect a twofold nature for this. So there'll be an answer when n is even and an answer when n is odd, because the cosines behave differently then. So let's just think through it here. So when n is even, again, the signs won't make any contribution. So when n is even and we're, well, when you evaluate at 0, you see there's a factor x here, so this will rub this out too. So the first integral, the only non-zero bit you get when n is even is when you subtract the evaluation at minus pi. So that's going to give us 1 over pi here at the start. 2 times n. X is evaluated at minus pi, but we're subtracting this because it's the lower limit, so let's just call this a pi. And then that's cosine n is even cosine n pi. I could probably have replaced that as 1. So when n is even, this cosine of minus n pi, that's always going to be plus 1. So actually I'll just scrub that there at the moment. And this is all over the denominator n cubed. So that's actually going to simplify somewhat to 2 over n squared, isn't it? Yeah. Now when n is even, okay, so but that's just from the first integral. When n is even and you come down here and you look at the second integral, does that contribute anything? Well, the signs won't, because they're always 0. So cosine of nx might contribute something. But when n is even, cosine of an even multiple of pi is going to give us a plus 1. Then we're going to be subtracting cosine of 0, which is subtracting 1. So you can have a plus 1 minus 1. So actually it won't, it'll cancel itself out. So we don't get any contribution from the second integral in the case where n is even. So when n is even, you're just left with this term here, which is going to simplify to 2 over n squared. When n is odd, we will get something. When n is odd, what are we going to get? Well, again, nothing from the sign, nothing from in this first integral when x is 0, because there's a factor of x here. So when n is odd, you've got cosine of an odd multiple of minus pi. So that's going to give us minus 1. Minus 1 from this cosine factor. It's going to multiply by x here, which is minus pi, so those will cancel out. Sorry, my computer screen's just gone off. I'll just wake it up again. It's better. So we get a minus sign here from x at minus pi, another minus sign from cosine of an odd multiple of pi. So they cancel out, but then we're subtracting the whole thing because it's a lower limit. So in total we're going to get minus, and there's the 1 over pi and the pi, but they'll cancel out. So you get a minus 2 over n squared. Minus 2 over n squared there. That's from the first integral. From the second integral, when n is odd, well, then we do get something, nothing from the sign again, but then we get something for these cosines. So cosine of an odd multiple of pi is going to give us negative 1. And then we're subtracting cosine of 0, so it gives us another negative 1. So we get a minus 2 factor from this. But this minus 2 is multiplied by this pi over here. Of course, then cancelled out by dividing by pi, but it's still over n squared. So we seem to have another minus 2 over n squared contribution there. So in total, when this comes out, in the case of n even, we simply have 2 over n squared. n is even. And when n is odd, we have minus 4 n squared when n is odd. So those are our coefficients an. Okay, so the main pitfalls there are all these plus and minus ones floating all over the place that you just have to keep very careful track of. It did take me a couple of goes to get it all straightened out. Okay, so we've got one more set of coefficients to determine, which are the bn's. So again, we go into it in the same way. We're going to have a similar expression to this up here, but just involving the sine functions. So bn is 1 over pi times the integral from minus pi to 0 of x squared times sine nx. So what I'm starting from here is the original coefficient formula for bn, but the behavior of f, remember, is it's got a certain behavior in the negative half and a certain behavior in the positive half. So that's why we split the integral up like this. First integral, and then 1 over pi times the integral from 0 to pi times x sine nx dx. Again, we can pass to the computer to help us out with these integrals, just to save us some time. So I'm just simply replacing these two cos functions with sine functions, and you get kind of similar expressions here for the integrals, but the roles of sine and cosine have kind of swapped around. So let's return to our paper here. So the expressions we're going to get, now I will just shortcut this a little bit because, but it's a similar deal to working with these expressions here. But I'll just put down the final result that we get. So again, when you look at let's just look at the expressions we got for the integrals. You know, when you're evaluating sine nx at 0 and pi, it's never going to give you anything. Anywhere where there's a factor of x, when you evaluate that at 0, that's not going to make any contribution, that particular term itself. So the only things that survive are when you're evaluating cosine at 0 or cosine at n times pi. And again, that's going to give you plus or minus 1, depending on whether n is odd or even. So you just have to keep track of all those contributions carefully. But when it all comes out in the wash, what you find is that when n is even, everything cancels out and you just have 0 here. And when n is odd, we have 4 over pi n cubed. Okay, so you can take that as a little exercise to work through those integrals and the evaluations, and you should get these expressions here. 0 for bn when n is even, and 4 over pi n cubed for bn when n is odd. Okay, so we've kind of succeeded there in doing that job. This function f will have this Fourier series, okay, involving these coefficients here. Where we've got this constant coefficient a0, which gets further multiplied by a half here. Then these expressions here, when n is even or n is odd, for an, and bn, well, only half of the bn survived, just the ones with odd index as well. So let's just check our calculations here. So we'll check with the computer to see whether all these coefficients are correct. Okay, so we'll go back to our Sage worksheet here. So what I've actually done here is I've prepared two little functions here. These are little functions that are going to called a and b. They're just going to take an input n, and they're just going to return the appropriate Fourier coefficient. So if you look back at the notes, so for the an, when n is even, so the definition of the function an here is if mod n2. Now mod n2 is the modulus, is the the value of n modulo 2. So when that's 0, in other words when n is even, we're going to return 2 over n squared, which is what we worked out for an when n is even. Otherwise, n will be odd, and we'll return minus 4 over n squared, which was the odd case value for an. I've got a similar function here for bn. If mod n2 is 0, in other words n is even, I'm going to return 0. That's what we worked out for bn. And when otherwise, else, if n isn't even, for evaluating this at integers, n will be odd, so I'll return 4 over pi times n cubed. So executing these statements here doesn't give us any output, because it's just defining these two functions an and bn. And then down here I've got some Sage Python code to illustrate this whole thing here. It's so this little decorator here at interact produces an interactive object. It's controlled by this slider here. So the slider allows us to select values between 0 and 15 in increments of 1 for the parameter m. M is going to be the upper limit in the partial sums for these kind of intermediate Fourier series. Not the whole infinite series, but to just going to the upper limit m. So what this interactive widget here does is it generates the plot. So this black function here is our original function f, so using the similar plotting commands as we had before. And then the loop here, when the value of m is reset, it calculates the partial sum Fourier approximation to the function f. So I've stored that in this symbolic function for FOUR, short for Fourier. So the constant coefficient, which will always be there, is a half times 5/6 of pi squared, which we worked out on the page. And then I have a little for loop here, which will loop in the range of values between 1 and m. This upper limit here for the range construction is a strict upper limit. So this will give me integer values of j in the range 1 up to and finishing at m. And then within this for loop here, I redefine the Fourier expression for x as what it was plus the term aj times cosine of jx plus the term bj times sine of jx. So that will build up, as that for loop runs, that will build up the mth partial sum of the Fourier series for f. And then the output that this widget gives us, I add the plot of that Fourier partial sum, colored red, to the plot that I had of the function f, and then I show f. I show that plot there. So when we start off, m has the value 0, and so this for loop here for j won't get executed at all. So we're just left with what we see is the constant approximation to the function f. And this, you can see that this I mean, it just appears roughly that red level is more, we wouldn't be surprised to learn that that's the average value of the function f across the whole range. And then as we start increasing m, so if I put m up to 1, so it's including one of the cosine functions and one of the sine functions. And so here's the red Fourier approximation to the function f. It's already doing a pretty good job of approximating the function. And as you increase m up to the values 2, 3, what we're seeing and so on is we get more and more terms added onto the Fourier series approximation. So our red function there is approximating the original function f of x better and better. And by the time you get up to the 10th or 11th partial sum, it's hard to discern any difference between the two functions at all. The only place they're kind of deviating significantly is at these 2 points of discontinuity of the derivative of f. That's where the Fourier series struggles a bit to get good approximation. So at the endpoints of the interval, and well, you can't really see it very clearly, but around 0 as well, there's still a bit of discrepancy. But by the time you get up to this maximum possible value we've allowed for here of 15, you've got very good agreement between the Fourier series in red and the original function f. Okay, I hope you found that useful, but this kind of exercise with Fourier series, I think you'll find some good preparation. Okay, bye.